Okay, let's get started. So today we have Professor Qiaomin Xie from University of Wisconsin-Madison. Qiaomin is an assistant professor in the Department of Industrial and Systems Engineering. She was previously visiting assistant professor at the School of Operations Research and Information Engineering at Cornell University. And prior to that, she was a postdoc researcher at LIS at MIT. Qiaomin received her PhD degree in electrical and computer engineering from University of Illinois, Urbana-Champaign in 2016. I actually know her when she was a PhD student, and I've been following her research since then. So she has done outstanding work in cloud computing, in reinforcement learning, and she is a recipient of the JP Morgan Faculty Research Award, Google Systems Research Award, and the UIUC CSL PhD Thesis Award. Today she's going to talk about best of three worlds. Okay. Yeah, go ahead, Qiaomin.
Thank you, Ray, for the nice introduction. And likewise, my work has been inspired a lot by your work, both on cloud computing and reinforcement learning. And thank you for inviting me here. And thank you for getting up so early to attend my talk today. So I know the title of my talk is a little bit wrong here. So I will pass the title and you will see what each term means as we go around. Okay. So one thing I want to highlight here. So one is the constant step size. The other one is the stochastic approximation. This talk is maybe, it seems like it's not working. I guess maybe it's out of battery. Sorry, guys. No, it doesn't work anymore. Oh, well, I guess I need to be here. Oh, okay. So this talk is mainly based on our recent paper. It's just got accepted to ACM Sigmatrix this year. And this is based on the joint work with Lucy Hall. She's currently a PhD student at Cornell. And my colleague Dongchen from UW-Madison. So what is the stochastic approximation? As I say, that's one of the keywords in my title. So the goal here is very simple. You just want to find theta star that solve the equations here. So basically, you want to find the root of this function, f bar. And here you can think about theta as the d-dimensional vector. And f bar here, this is the function mapping this d-dimensional vector to a d-dimensional vector. Okay. And so here, in many cases, we may not be able to know the exact f bar function, but we may have access to a sequential noisy observation of the function f bar. So then the stochastic approximation basically is just an iterative method that help us to approximately find the solution theta star based on the noisy observation. So in particular, given the constant observation fk, it's going to update the estimates for the theta k in the following way. And here the alpha k, typically we call it step size. And of course, in the machine learning community, typically called the learning rate, which sounds fancier, and that's what students prefer. So here basically it represents the weights you give to the constant noisy observation, okay? And it can be depending on the iteration k. So this is the very general procedure, and actually stochastic approximation have many applications. And one well-known domain is on optimization. Say, suppose that you have a function f and you want to minimize this function. So think about this is the loss of your neural network, and that you want to, and theta corresponding to the parameter of your neural network. And suppose the function is nice enough, it's convex, then we know this is equivalent to finding the solutions to the gradients of the function f. Okay, so now the f bar function is just the gradient function of your objective function. And now we know then in this case, the SA procedure is just reduced to the so-called SGD, the stochastic gradient. In particular, typically we don't have access to the exact gradients of the function, but we may have access to a noisy gradient, say based on the mini batch of your samples. And so this is just an initialization of this general SA procedure. So this is the well-known example. Later, we will see another application domain is in reinforcement learning. Many reinforcement learning algorithms, including the popular TD learning, Q learning, they all can be cast as an instance of the SA procedure. And we'll get into a little bit more detail how we can rewrite the TD learning as the SA formulation. And the questions we want to address in this talk here is how this SA procedure work if we use the constant step size across the, all the iterations. Okay. Yeah, what if we used all the step size alpha? So there are several reasons why we are interested in this problem. So in practice, so if you have played around with the neural network, you know, if you check the code actually, so typically they will have a default value for the step size. And then usually it will run, say, like 10,000 iterations, and or maybe depending on the problem, and then it will gradually decay the step size. So decay maybe by a factor of 2 or maybe by a factor of 10. And then run the new, reduce the step size for another, say, 10,000 iteration, and then reduce the step size again. So repeats this process. So the question that's what one motivation we're interested in this problem. And there are several reasons why people want to use constant step size. So first, it's easy to use. So if you don't need to tune the parameter so much. And later we will see there's some benefits of using constant step size in terms of a convergence rate. Okay. So just a preview of our results here. So I hope our result can be summarized by the following 2 plots. So here we run the SA with different constant step size. So different color corresponding to the different step size here. And the x-axis corresponding to the iteration, and the y-axis corresponding to the error, to the true solution. And so there are a few observations we have here. So first, no matter what, so for all these different step size, all the sequence eventually converge. Okay, so that's so we know, so we observe the convergence, it becomes flat. Okay. Second, even if the iteration continues, so as the iteration goes along, so the error doesn't decay with the iteration. It remains a constant step. Okay. So in particular, the one additional observation here is, so here in this direction, we can see, so the intentionally use different color here. So corresponding to, so the step size is decaying in this direction. And we can see the error actually kind of proportionally decays with the step size. Okay? And so the using larger step size actually induced a larger bias or larger error. Okay? In particular, our results provide a clean and precise characterization on the bias, showing how the bias depending on the step size you choose. Second, now, so here this is more on the asymptotic phenomenon of the iterates. Now let's look at the finite convergence rate here. So one thing, so here in kind of contraries to the stationary behavior of the bias. So the convergence rate here is actually, so if we use a larger step size, it's actually converge faster. So maybe a little bit difficult to see here. So the bottom line here actually corresponding to the largest step size. And I cut off the iteration from the previous step, but later we can also have a closer look. So the short message here is if you used a larger step size, it will allow your iterates to converge faster. But the price here is you will incur a larger bias or larger error. So that's why, as I said earlier, so in practice, why usually they will run the constant step size at the beginning. So in this way, you can have a faster convergence. But then in order to further reduce the bias, then when it's almost stationary, they tend to decrease the step size in order to achieve the small bias. So that's the 2 observations here. So now you can see, so all these iterates, if we use constant step size, the error is relatively large. Okay, the order of like about like 2 error of 2 here. So so here this is just the same process as the previous slide. I just zoom out the process. We're using a different scale. Now thanks to our analysis for bias, we can actually build on these larger error estimates to construct a new estimate. So, and in particular, the new estimates, as shown in the blue curve here, can significantly reduce the bias. So we will see how we can have this magical tool by looking at the exact analysis of a bias. Okay. So this is our 2 main results in this talk. So I hope the 2 parts to give you some visualization of how we can interpret the results and how we can use that. Okay, now I'm ready to formally introduce the problem. So in this talk, I'm going to focus on a particular class of stochastic approximation. In particular, here we want to approximately solve a set of linear equations. And again, so here the A bar and the B bar are unknown, but we may have access to a noisy observation of these parameter. So you can think about theta is the d-dimensional vector, and the A bar is the d by d matrix. And the B bar is also a d-dimensional vector. And now we may have access to a noisy observation of these 2 parameters, the A bar function and the B bar. And in particular, the observation we have depending on Markov chain. So Markov chain xk. And in this talk, we assume the Markov chain has an unknown stationary distribution. And the A bar and the B bar corresponding to the expectation of these the noisy function with respect to the stationary distribution of the Markov chain, the Markov chain distribution at pi. Okay. So now in this linear function setting, then the SA procedure reduced to the following update. So we know, so this just corresponding to the FK we mentioned earlier. So the FK we can see is just a noisy observation of the true function f bar. And transfer. So there are 2 special cases of the yes.
So the XK are generated with this unknown stationary distribution. So we assume the Markov chain is already in steady state.
So it doesn't really matter it's already in stationary state or not. So here we as you will see later. So we assume the Markov chain will mixed geometrically fast. So at most you will just lose the first a few episodes, a few iterations due to the mixing time of the chain. Any other questions at this moment? Okay. So this is the iteration we are going to focus in this talk here. And we will focus on the constant step size. So just to give you some idea what this RSA example can be. So one special case is the SGD we saw earlier. So now in this case, the objective is actually corresponding to a quadratic function. Okay, so have we this the A bar and the B bar function. And so this is actually just the least square problem. So in this case, we know, so the is equivalent to solving the gradients, the function, to get the roots of the gradient function. And in particular, so in general, you might be familiar with the SGD with i.i.d data. But in many applications like sequential decision-making problem, like in the domain of reinforcement learning, in many cases, we only have access to Markovian data. So that's typical. And in this case, then the SGD just becomes perform the following updates here. And again, here AK and BK are noisy observation, and the expectation corresponding to the true parameter in your objective function. So approximately, it's to try to solve the first order condition for the optimality. So this is the one example. And the other example is in reinforcement learning. I guess many of you are familiar with this. So we know reinforcement learning is about the study of sequential decision making. And typically that's an agent interacting with an environment. In particular, at each time step, the agents will take some action, and then the environments will generate the reward as the feedback signal. And it will also make a transitions to a new state according to some Markovian kernel. And then such interaction will continue and repeat. And in particular, here the policy for the agents basically map each state to a distribution over the action space. So it specifies the probability of taking a particular action given a constant state. And in general, the agents that want to find out the policy that's optimize the total discounted reward. And here that's considered a simpler problem in reinforcement learning. So the so-called policy evaluation problem. So you have a target, a particular policy sigma, and all you want to do is to estimate the corresponding value function. And in particular, here the value function is just the total discounted reward that the agent can get by following this particular policy sigma. And why this problem important? So in reinforcement learning, many algorithms, say like actor-quick algorithm and the policy gradient optimization-based algorithm, they all rely on have a subroutine, the policy evaluation. So if it's important that you can do these steps efficiently. Okay, so to just provide some background. Now, if you know everything about this model, so if you know the reward function, if you know the transition kernel, then you can try to solve the value function exactly by using dynamic programming. In particular, it's well known the value function here satisfies the so-called Bellman equation. So equivalent states can be written in terms of some linear function with respect to the value function. So if you know everything about a problem, you can just solve this equation exactly. But in many cases, the model is unknown, but we may have access to a sequential data generated by the policy. So TD learning is actually one such algorithm that aims to estimate the value function based on a sequential data. And for example, the data can be the trajectory generated by the target policy that we want to evaluate. And the data typically in the form of constant states, the reward you can guess, and the next stage formality. And given every time, given such a tuple of the data, the TD learning is going to update the estimates for the value function in the following way. And in particular, the highlight part is so-called temporal difference. So it's basically just measure the difference between your new estimates you can get based on the constant data and your constant estimates. So that this is exactly what the name, the TD learning coming from. So of course, here I'm just talking about the tabular setting. So you can generalize these settings to accommodate the function approximation. So you can use linear function approximation to deal with the large state space and action space. And it turns out this update rule of TD learning is actually corresponding to a special case of the general SA we introduced earlier. The theta k parameter we want to estimate just corresponding to the value function you want to estimate. And then the Markov chain that driven the noisy observation just corresponding to the underlying Markov chain that's generated data you observe. And you can have equivalent expressions for this A matrix and the B function. And as I say, so there can be other variants of TD learning, say for using function approximation, and say you can also use the multi-step data to update your value function as well, corresponding to the TD lambda. And it turns out all these variants, they can be written as the special case of the general RSA procedure. So these are two examples of the RSA procedure we discussed earlier. And that the study of RSA actually has a long history. So it dates back to the seminal work by Robbins and Morons back in 50s. And the classical results that mainly focused on using diminishing step size. So in particular, so typically the step size are required to satisfy these two conditions. So the summation of the step size should be infinite, but the square of the step size should be summable. And one example of the step size scales to 1 over k with the iteration. So, and in general, you can choose the k to the power of, say, a beta, and as long as the beta between 0 and 1, and typically these can satisfy this condition. And under such diminishing step size, prior work shows that the RSA or general SA can converge asymptotically to the true solution, to the theta star, as the number of iteration goes to infinity. Okay, if you impose some condition on the underlying, the original problem you want to solve. And it's nice to have these asymptotic results, but in practice, we only have limited sample data. So we care about the sample complexity. So in particular, like in reinforcement learning, we care about how many samples we need in order to obtain, say, an epsilon accurate value function. So we care about its importance to have non-asymptotic guarantee of the procedure. And actually, recently there has the significant advanced on the non-asymptotic results. So I just want to highlight some related work here. So it's definitely an incomplete list. So one simple setting, consider the case if your data have i.i.d. So meaning your noise is also i.i.d. So that's corresponding to the case the SK is sampled independently from some distribution. And in under this setting, so prior work mainly focused on getting an upper bound on the mean square error. So the results that you might have seen that might have form like this. So if you use the decaying step size, then the mean square error will roughly be upper bounded by the in terms of the iteration in this way. So the beta here corresponding to the exponents you used in your step size in the diminishing case. And later we will see what will happen if we used a constant step size. And some other work tried to establish the concentration results in this form here. And in particular, the very recent work by Zaiwei Chen, Siva Manganari, Martin, and Jubaria, they establish an exponential concentration tail bound for the iterate for a general contractive SA. It's a very nice result. And for, as we say, for the sequential decision-making problem, in general, it's difficult to have this i.i.d. observation, but instead the data may be driven by some Markov chain. So it's more a more practical and reasonable setting to consider. And prior work also consider this practical setting, and including the seminal work by Lei and Strickland on the TD learning analysis. And most of the results you will see from this paper try to give an upper bound on the MSE. So like the in the i.i.d. setting, but typically it also provide an upper bound on the mean square error. Okay. And in this talk, we will also focus on the setting with Markovian data, but we will focus on the setting where we use the constant step size across the different iterations. And there are a few key observations here. So as we saw earlier from the two plots, if we use the constant step size, the theta k actually will not converge to theta star. And later we will see actually the theta k will kind of like oscillate. So it will kind of oscillate around the true solution theta star. And in particular, the way we can try to analyze the limiting or the transient behavior of the theta k is by looking at the joins the Markov chain that's formulated by both the xk that generates the data and the parameter theta k sequence together. So under the importantly, only under the constant step size, these two parameters together can form a time homogeneous Markov chain. So in this way, we can leverage the tools from the Markov chain theory to help us analyze the behavior of the parameter sequence. So in particular, we will show both the existence and uniqueness of the stationary distribution for this augmented Markov chain. And we will also establish the convergence, the raised the convergence rate of the Markov chain. So by analyzing the joints, the Markov chain, then this allows us to establish the convergence of the parameter theta k sequence, which is what we are interested in. Okay, so the SK itself is just generating the data, but in order to analyze the theta k, because itself is not a Markov chain, so we need to analyze these two components together. And then we will see how we can show the convergence of the theta k sequence. So just some highlights on how we can analyze this sequence and what kind of results we can expect. Okay, so to show the results, we need some assumptions. So the first assumption is on the Markov chain that's generated data. So for simplicity, that you can think about the Markov chain SK is only on a finite state space, and the corresponding Markov chain is irreducible and aperiodic. And an immediate result of this assumption here is the SK has a unique stationary distribution, and in particular, it will converge to this stationary distribution geometrically fast. But we recently actually generalized all our results to the general setting with infinite state space and even unbounded, even continuous state space. But for simplicity, here we just focused on finite state space here. The second assumption is on the underlying problem that we want to solve. So in particular, we assume that the A bar matrix is Hurwitz. So Hurwitz means if we look at this matrix, is eigenvalue, all eigenvalue has negative the real part. Okay. And if the matrix A bar here happens to be symmetric, then this condition basically saying this matrix is a negative definite. So just some example what this condition means. So in the SGD case we saw earlier, this just means the objective function is strongly convex quadratic function. And in the TD learning setting, if the problem we want to solve is the discounted MDP, then it will automatically satisfy this condition as well. And an immediate implication of this assumption here is that exists some symmetric positive definite matrix gamma that satisfies this so-called Lyapunov function. And the way why I call Lyapunov function is coming from the control theory. And later you might see some two parameters, which I don't know by gamma min and the gamma max. That's corresponding to the minimum and the maximum eigenvalue of the gamma matrix. Okay. So it's depending on the parameter of your original problem you want to solve. Okay. And under these conditions, so you can also see the original problem. So the linear function we want to solve actually has the unique solution theta star. That's also coming from this assumption too. The last assumption we imposed is on the more on like a regularity assumption. So we here for simplicity, we assume that the noisy sequence that we have are all bounded in some norm. So here the vector is upper bound. So here we consider for the vector B, we consider that's Euclidean L2 norm. And for the matrix, is that we use the spectral norm here. So under this, so these are the three key assumptions for our main results. Any questions up to this point before I continue? Okay. So the first result we want to have is to show the alpha k, the theta k sequence will converge. And in particular, we want to show that the theta sequence will converge to a unique limit independent of the initialization. It turns out in order to show this distributional convergence, it's crucial to choose a proper distance metric on the distribution. And it turns out if you just use total variation distance, that doesn't work. And you can actually construct a very simple counterexample to show if you use TV distance, then the distance between the theta k sequence and the limiting distribution will not converge. So that's why it's important to choose the proper metric in order to show the result. So in particular, we use the two Wasserstein distance. So this is the formal definition for two Wasserstein distance. So here in particular, here mu and nu are just two distribution. So basically, consider all coupling between the mu and nu. So basically, you can think about that's a joint distribution, and with the marginal distribution being mu and nu. And here it computes the distance between these two parameters under this joint distribution. And actually, if you heard about the optimal transport, the two Wasserstein distance have a nice interpretation with respect to the optimal transport between two distributions. And it's also used in many other modern machine learning analysis. Okay, it turns out that it's important to use the Wasserstein distance to establish the distributional convergence.
So why we are interested in distributional convergence? Can we just look at the the mean square error between theta and the theta star?
But that will only give the mean square error.
Right. But what additional information the distributional convergence?
Very good point. So later, in order to capture the limit, we need to deal with the distribution. Yeah. So if you just look at the mean square error, that doesn't give you a precise characterization of the limit. So we will see that later. Very good question. Okay, so under the three assumptions we saw earlier, then if we choose the step size properly, so here the tau corresponding to the mixing time of the Markov chain, let's generate the data. So basically just saying if we choose the step size small enough, then we can show the joins the Markov chain between xk sequence and the theta k sequence will converge in distribution to a unique limit independent of the initialization. And the limits distribution actually just have the marginal distribution for the xk sequence. So we know the marginal distribution for sk just is stationary distribution by itself. And the marginal distribution for the theta parameter, here we denote by mu alpha, which depending on the step size alpha. Importantly, we can further show that. So here we first show the joint convergence of the augmented Markov chain. And then we can show that the distribution of the theta sequence at the iteration k. So here we denote this is the distribution or the law of the theta k. And the distance between the distribution and the limiting marginal distribution actually will decay geometrically fast in the Wasserstein distance of order 2. And here the geometrical rate will depending on your step size you choose. That's also kind of like what we saw earlier. If you choose different step size, it will show different convergence rate. Okay. And a few kind of corollary or implication of these results here is first, we can have the geometric convergence of the first moment and the second moment. And thanks to the geometric decays in the Wasserstein distance. And the proof idea combines the Lyapunov-driven analysis, which is inspired by Lei's work on the TD learning analysis, and by a special Markov chain coupling. So in particular, it's turned out if we just use the results from Lei's paper, it's not enough to show these results. So we need to refine your analysis and to get a tighter bound, and by using a particular Markov chain coupling. So that together allows us to establish this result. So now comes to Lei's question. So here we have the why we care about the distribution. So because we want to understand the limit. So here because the limits, so first here we will consider a particular variance of average tail averaging. So it's the variance of the so-called polyhedral loop averaging. But instead of taking all the average over all the iterates, you only average over the, say, the last many iterates. Say, for example, maybe you can discard the first half of the iterates and only average over the second half of the iterate. That's why it's called the tail averaging. And now by the law of large number for the Markov chain, then the tail average you can show it will converge to the expectation of the limits in when expectation of the limit. So here the expectation with respect to the marginal distribution of the theta in when the Markov chain is in stationary. And the one question we are interested here is, so will the averaging iterate give us an unbiased estimate of the true solution theta star? And of course, as we saw earlier from the plots, the answer is no. And this is kind of like why we care about the distribution. So because if you just focused on the mean square error, this will not give us the precise characterization of how these limits will deviate from the true solution theta star. And in order to understand the bias, we are going to based on the results on the distributional convergence of the theta sequence. So in particular, as we saw earlier, so it will induce, so it's not it's a biased estimate of the true solution. But then the question is, how large is the bias, and how the bias depending on the parameter of the problem, and how it depends on the step size that you used in the iterate. So precisely, so under the same Sasser condition, we can show that the bias between the average iterates and the true solution will scale with the step size as follows. So now you can see if the step size is small, then the first term becomes the dominating term in the bias. So roughly, when you use the relatively small step size, then the bias roughly will scale proportional to the step size you use. And in more generally, we can actually have a Taylor expansion like of the bias with respect to the step size. And one important thing here is the coefficients, the coefficients, the B1 here, and all the general coefficients, the BI, they are all independent of the step size you use. But it can depending on the underlying problem parameter, say the A bar, B bar, and also the transition kernel of the Markov chain that's generated the data. Okay. And later you will see why the independence of the step size is important. Okay. So the two key messages here is, so if we just average over the iterates, they will not eliminate the bias. So in particular, it does not converge to the true parameter theta star you want to estimate. And additionally, so if you use the relatively small step size, the bias will scale linearly with the step size we use. And that's also consistent with the phenomenon we observed earlier. The larger step size you use, the larger bias you will have. Okay, so now let's try to compare the results against the setting when we use the i.i.d data. So here, these two, the left hand, the plots on the left here, this corresponding to the dependence graph if we have i.i.d observation. And in particular, so here the theta k here will truly only depend linearly depending on the previous estimate theta k. And all the data here, they are i.i.d, so it does not, there's no cross dependence here. But now on the right-hand side, this corresponding to the setting, if the data have this Markovian dependence. So one important thing here is for the theta k parameter at the next iteration, it will depending on the theta k, so through the linear update, but also it will have implicit dependence due to the Markovian correlation in the theta k in the xk sequence. And in particular, so if we use i.i.d data, then because the sk sequence they just i.i.d, so the theta k itself is just form a Markov chain. You can just analyze the theta k sequence itself, and it turns out even if you use the constant step size, it doesn't have no bias at all. So as long as you choose the step size properly, then it will guarantee to converge to the true parameter theta star you want to estimate. And that's actually kind of like what you expect if you use the SGD for the quadratic or the least square of the problem, if the data truly are i.i.d generated. Okay. So one main reason is the theta k here only truly linearly depending on the theta k from the previous iterate. But now for the Markovian data setting, so as we saw earlier, so the bias will be proportional to the step size. So to the end, where the bias comes from. So we know if there is no correlation across the SK sequence, there is no bias at all. But the correlation, so here the theta k, so we know according to the updates, we're depending on the theta k, but the correlation across the theta xk will create an additional and implicit dependence between the iterate. And this is exactly where the bias come from. So now you might wonder, so in the extreme case for the Markov chain, so if the Markov chain mix really quick, then it almost like i.i.d setting. Then in this case, you do not have any bias at all. But intuitively, if the Markov chain mix slowly, meaning the iterates of the xk here have strong correlation here, then you might intuitively expect this strong correlation will induce the strong extra correlation and the results a larger bias. So we can formally capture this phenomenon showing how the bias depending on the mixing time of the underlying Markov chain SK. So intuitive in the extreme case, so if it's just i.i.d, then there's no bias at all. But in the other case, if it mixes very, very slowly, then we can expect a larger bias. Okay, so that's the intuition. And formally, we can analyze so how the coefficients here, depending on the mixing time of the Markov chain SK, that's generate the data. And in particular, so under the same set of assumptions, we can show that the coefficients here, B1, will scale depending on the eigenvalue modulus in this particular way. So here, lambda 2 is the second largest eigenvalue for the transition kernel of the Markov chain SK that's generated data. And so one nice thing about this lambda 2 is that they have a nice connection to the underlying mixing time of the Markov chain SK. In particular, so roughly the lambda 2, the modulus of lambda 2 will roughly proportional to the mixing time of the Markov chain SK. So if we have a larger, if the Markov chain have a larger mixing time, then so it's roughly implies a larger modulus of lambda 2. And then from the formula we have here, you can see a larger lambda 2 actually implies a larger bias. So that's also, and in the other extreme, if the Markov chain have a really fast mixing time, very small mixing time, then intuitively it implies the small lambda 2 modulus and implies the small bias. And of course, in this extreme case, if data is truly i.i.d, then the mixing time is 0. So, and then the lambda 2, the largest, second largest eigenvalue of the modulus of 0, then it's reduced to the 0 bias in i.i.d setting. So in short, our results actually subsumes the previous results on the i.i.d data case, but to be more general to allow the Markovian data setting. Any questions up to this point? Okay, so here these plots, we try to illustrate how the bias depending on the mixing time of Markov chain. So we tested different Markov chain with different mixing time corresponding to different modulus of the second largest eigenvalue. And you can see, so in this direction, so the bias will decay with lambda 2. So in this direction, the lambda 2 becomes smaller. And the yellow curve corresponding to the case, there is no bias at all. That's why you see it's still decaying. And if you further run the iteration, it will continue decaying to a smaller value. Okay, so now if we put everything together, the tail averaging and the bias characterization, then we can have the following first moments and the second moments for the tail average iterate. So that's me pass the results for the first moments here. So as we say, the averaging iterates does not eliminate the bias. So you can expect the bias will be similar to the limits of the expectation. So we have similar order of the bias scales with the step size alpha. And for the second term, this is what typically they call the optimization error, just due to the finite steps iteration. And typically the optimization error we have here, so it's nicely decayed exponentially fast with the iterate. This is due to the use of the constant step size. If you just use diminishing step size, you will not be able to have this exponential decay of the optimization error. And in particular, the convergence rate is exactly the convergence rate of the distributional of the theta k sequence with respect to the limit in the Wasserstein distance too. And similarly for the second moment, so we have three terms of the error. So the first term is also due to the bias, so it's the bias of the square. Second term is due to the variance of the theta k. And the last term is similarly is also due to optimization error. So now you can see if we have for k large enough, then the bias become the dominating term. So then the question here is there any way we can try to reduce the bias by using our results here? And one important thing here is we know the coefficients here are fully independent of the step size. So this allows to use the magical tool I showed earlier, the extrapolation, to reduce the bias. So in particular, so you can run the iterates using different step size. So here I choose the steps alpha and the 2 alpha. Actually, you can choose any other 2 different step size. Okay, and you can run these 2 iterations totally independent in parallel using exactly the same sequence of the data. So you don't need to get the extra data for the different iterate. Now with these 2 iterates, we can construct the so-called Richardson-Lumberg extrapolation sequence. It's just the linear combination of the 2 iterates by using these 2 different step size. It will become clear why we choose the coefficients in this way. So first, R extrapolation is actually a de-bias technique used in numerical analysis, but it's not so used not so much in the machine learning community yet. And so because that's for each iterate, we know roughly the bias we proportional to the step size. So the first one, we have the step proportional to alpha. And the second one, because we use the step size to alpha, so the bias roughly scale with to alpha. Now, if we choose the coefficient 2 here, then this will allow us to eliminate the bias, and we only reduce the bias to higher order dependence on the alpha. So that's the idea we use to reduce the bias by this R extrapolation. And in particular, so we have the following results for the new iterates we construct by the R extrapolation. So in particular, I want to point out here, the bias now can reduce from alpha to alpha square. And similarly, for the second moment, then the bias is reduced from alpha to the power of 2 to the power of alpha order 4. So now you can see just by using these running 2 iterates, you can significantly reduce the bias. Okay. And here is some numerical results here. So the dots corresponding to the raw iterates without any averaging. So the dashed line, so here we can see the 3 step size. So 0.4, 0.4 and 0.2 here in this decreasing order. So you can see, so using smaller step size to have the smaller error. And now let's show, see the R extrapolation sequence. So the red solid line using the 2 step size, the blue one and the red one. And now we can see it significantly reduced the bias here. And for green one, is use the 2 iterates, the red one and the green one here. And we can see it's also reduced the bias. Okay. So here we only use 2 iterates to reduce the bias. And because that we actually have any finite order expansion of the bias with respect to the step size. So in general, we can actually use the higher order extrapolation to further reduce the bias. So we have this the any finite order extrapolate expansion. Then we can actually run the iterate using multiple different step size. Say use alpha 1 to alpha m, and as long as they're different, then you can properly choose the coefficients to construct an extrapolation sequence. Then we can reduce the bias by eliminating all the first m-1 leading terms in the bias. And at the end, you only end up with the bias that's scaled into the power of m. Now, so you can see the larger m you choose, then the further bias you can reduce. And so one important thing here is all these different iterates, they can be fully run in parallel. So using the same sequence of data, so you don't need a new extra data at all. So you just use the exact same sequence data. So in this way, you can kind of use the computation to buy us some kind of sample complexity. So by reusing the data to improve the estimates of the parameter.
What knowledge you need to have to compute H here?
So actually, you can. So here, you don't need to know all these the parameters as long as you know they are constant, not depending on alpha. Then you can set up the set of linear equations to solve the coefficients HI. So basically, you want to set up the equation such that all the first m-1 order that eliminate.
Mm-hmm.
So these will set up the equations for this HI parameter. Actually, so if you choose the alpha sequence to be in the geometric order, then this corresponding to solving a van der Waals equation. So you can actually easily obtain this parameter here. And this does not record any information about the parameter of the constants B1, B2, as long as they are constant, not depending on alpha. Yeah. And one important thing here is because no matter what the step size you use, they're all the same constants. That's the reason why we can eliminate all the first m-1 order leading term. So these are numerical. I know it's a little bit crowded here. So it's exactly the same set of results we saw at the beginning. So the first set of line that's corresponding to the original iterate. So we're using these different step size. And the first dashed line set corresponding to the R extrapolation, but only using 2 different step size. So we can see it's reduced the bias. Now, if we use 3 different step size for the R extrapolation, we can see it's further reduced the bias. And this used the 4 different sets of step size. And the blue curve we saw earlier, that's the one we used all these 6 step size to eliminate the first m-1 leading term in the bias. And just as a comparison, so the pink one corresponding to using a diminishing step size with the 1/k order. And you can see comparing the diminishing step size and constant step size, the constant step size have the benefit of faster convergence. But of course, they incurs the larger error if you continue running that. Okay, so now this comes to the title of my talk. So putting everything together. So first, what we know from the previous work is if we use diminishing step size, then we can guarantee to asymptotically converge to the true value we want. But we need to, so in order to have a faster convergence, you need to carefully tune the other parameter in the step size here. And so our results kind of suggest an alternative paradigm for choosing the step size. So in particular, as we saw earlier, we can decompose the mean square error into 3 terms: the optimization error, and the bias, and the variance. So for each term, we can have tools to reduce the error. So for example, we can use constant step size to have the geometrical convergence of the optimization error. And we can use the tail average to reduce the variance, the averaging. And for the bias, we can use the R extrapolation to reduce the bias. So here we can combine these 3 techniques together to further reduce the MSD for our estimate. So that's the takeaway message of this talk here. I think I'm running out of time, so I'm going to skip the group. So, so just a summary. So this is the 3 techniques we discussed here. And there's some very interesting questions starting from here. So far, we only be able to capture how the bias depending on the step size and the mixing time of the Markovian. But we didn't say anything about the dependence on the dimension of the problem yet. So it's an interesting problem to think about what's the bias depending on the dimension of the problem. So here we can focus on the linear SA. So, but in general, there can be other stochastic approximation procedure for deeper function that are not linear. For example, like Q-learning is also an SA, but it's not a linear SA. It's the general contractive SA, so another class of SA problem. We make some progress on this path, and actually say for some contractive SA, we are able to generalize our results to the setting. And another very important problem, how can we use our results here to guide us to do the learning rate scheduling? How is it possible to design to have an adaptive learning rate such that whenever you are almost stationary, then you will automatically decay your step size. And we also make some progress on this problem by using by developing a new stationary detection. And in that way, so at least currently, the numerical results we have is the adaptive method kind of always kind of like getting the lower bound if comparing to all the constant step size we use. So we're currently formalizing the theory behind the technique. Okay, that's all I want to talk about here. Thank you for your attention, and I'm happy to take any questions.
So I have a question. So, if the approximation is not linear, how do we combine the parameter together?
So you mean the R extrapolation?
Right.
So it's exactly the same procedure. So the key here is how the bias depending on the step size. So in some setting, we are able to, even if it's non-linear SA, say like Q-learning, so it's a contractive mapping. And in that case, we can show under some condition, it still have this linear dependence on the step size. So in this case, you can use exactly the same extrapolation to construct the new iterate. And in other case, it turns out it also depending on the step size, but depending on the step size in a different way. It's not linear at all. But in that way, as long as you can capture how it depending on the step size exactly, then you can still construct an extrapolation to eliminate the lower order.
Yeah, I'm more thinking about like if we have neural network.
Oh, that's a very interesting question. A very excellent question, which I don't have an answer, unfortunately. Yeah.
Thanks.